Okay, we're gonna go ahead and start. Um, Tests are not graded yet. My goal is to get those done between today, tomorrow, and over Easter break. Um, Besides that, if you wanted to retake the trig test, you need to email me. I'm gonna have a plan for that for over Easter break, so you can get it done between now, or at least tomorrow or whenever I send it to you, and like Tuesday or Wednesday of next week. Okay, so you should have plenty of time to be able to do this. It does require a little bit more effort just because of the nature of how the test was originally given and um, how it is right now. So if you want to retake it, you need to email me. I'll also make that available to everyone tomorrow in an email. But it would be helpful to know like who is actually looking to retake it. Besides that, we're gonna start the last chapter that you guys have for me. Okay, so this will end, uh, and that will be the cap of the material on the final. All right, um, which is sequences and series, but a little bit more broad is probability. All right, so we're gonna be working for the next couple of days, the next couple of classes into probability. But before we do all of that, we have to set, uh, we have to get a couple of tools ready in order to deal with probability in its like whole form. All right. So that's what we're going to be working on these next couple of classes. If you haven't had a chance to write this down, you need to. This is really important. It's kind of setting the foundation for what we're going to be doing coming up. Okay, so I'm going to give people another 20 to 30 seconds just to write it down if you haven't, and then we'll get started. Okay, so as you finish writing this up, and you can continue writing. I'm just going to explain a couple of things on your screen. So we're going to spend most of the time talking today about sequences and series, which is really the foundation of what we will have to do coming up in calculus, and even later than that if you plan on doing anything with any remote math involved. Um, so a sequence is just any collection that can be numbered. All right, there's a first term, a second term, a third term, and so on. Okay, so again, anything that can be ordered in any way. So in math terms, it is a function whose domain is the set of positive integers. All right, so again, all that means is it's able to be numbered. All right, so we have function notation down here, and we have the notation that we're going to be working with coming up. Okay, so f of 1, that just means it's the first term. We're going to rewrite this as a1. F of 2, that's the second term. We're going to rewrite that as a2, and so on, right? So this notation with the a's and the subscript, that's called subscript notation. And we're going to be using that for the rest of the chapter. Okay, so that is kind of the definition of a sequence. Um, there are two different types. There's an infinite sequence, which is a function whose domain is the set of all positive integers. So it's just an indefinite um, sequence of things. So it can be numbered 1, 2, 3, all the way up until infinity. All right. If the domain is only some number, so it's not infinity, it stops at some point, that is called a finite sequence. Okay, so I want to pause there real quick. If there are any questions, now would be a great time to ask about what's on your screen. I will say that there are no plans of canceling finals. I don't know where you heard that SLU canceled theirs. I don't think that's true. Um, as of right now, I haven't heard anything about canceling ours. In fact, we're still doing them. We're just going to be doing them slightly differently. Okay. So definition of a sequence is everything in red. Okay. Now, there are a couple of different things that we'll have to be doing with this stuff. And the most simple is just finding different terms of a sequence. Okay. So what this says on your screen is what are the first four terms of the given sequence. And we are given a rule for the nth term in red, white, and blue. Okay. So we're going to work first with the white example. Okay. It tells us that our sequence is defined where the nth term is 3n minus 2. And we want to find a1, the first term, a2, the second term, a3, and a4. And all we're doing is substituting in 1, 2, 3, and 4 into that sequence and getting a number. All right, so a1 is just 3 times 1 minus 2. a2 is 3 times 2 minus 2. All the way down. And then obviously we just simplify. Okay, so this is like the most basic thing that we can do with sequences is just define a certain number of terms given a rule. And just one thing to notice, we don't have to worry about this just yet. You should be able to tell that there is a constant difference between terms. And when that's the case, this is called an arithmetic sequence, which we'll go over later, but it follows certain patterns. It has certain rules and certain sums, which we'll get to also in a minute. But just something to notice. So there's a definite difference between terms. Okay. The same is true for in red, but it doesn't always look the same. So it's not always going up. It's not always going down. Sometimes it can switch between just two terms. All right. So again, we want to find the first four terms. And all we have to do is substitute in the number of our term for n. Okay, and then we evaluate that. So 3 plus negative 1 to the first. This negative 1 to the first is just negative 1. So we have 3 minus 1, which is 2. Negative 1 squared, that's positive 1. So then we have 3 plus 1, which is 4. Negative 1 cubed, that's negative 1. 3 minus 1 is 2. Negative 1 to the fourth, that's positive 1. So this ends up being 4. Okay, so these sequences, they can go back and forth between just two terms. They don't always have to just go up. They don't always just have to go down. And even beyond that, they don't have to always have the same sign, and they don't always have to be just repeating numbers. All right, so in blue, again, we're trying to find the first four terms. And all we have to do is substitute the number of the term in for n. And when we simplify all of this, again, we have to pay attention to the sign. So we have to pay attention to the -1 to some power. So -1 to the first power, that's going to be negative. And then 2 times 1 plus 1 is just 4. Sorry, 3. -1 squared, that's going to be a positive 1. 2 times 2 is 4 plus 1, that's 5. And then it just keeps switching sign. And the denominator keeps getting bigger. Okay, so again, it doesn't always just have to go up. It doesn't always have to go down. It doesn't always just have to repeat. It can change signs, and then it can also get smaller or bigger, whatever. Okay. But we also need to be able to just plug in numbers and kind of use function notation. Okay, so I'm going to pause there for a second. Are there any questions about what you see on your screen? Okay, so in the previous examples, we worked from a rule for the nth term down to the sequence. So we got certain terms. We also have to be able to work backwards. So from the terms, we have to work to a rule for the sequence. Okay, so given the sequence, find the nth term, or give a rule or function for an, right? So in this case, we are working from the number of the term in blue down to the term itself, and we need a function in order to do that. So we'll have f of some number, and then we have to get to the actual term itself. So in order to do that, we have to figure out how to go from blue down to our actual term. And you have to look at kind of all the terms and all the numbers of the terms all at once. So if you notice as you go down along the line, if you just double the blue terms, you're very, very close to the terms themselves. So 1 times 2, that's 2. 2 times 2, that ends up being 4. 3 times 2, that's 6. 4 times 2, that's 8. So in each case, we're only 1 off of the actual term itself. Okay, and if we continue this, our next term, just by adding 2 continually, would be 9, 11, and so on. Okay, so if we extended this, the 5th term has to be 9, but 5 times 2 is 10, 6 times 2 is 12, and again, we're still just 1 off. Okay, so in each term, we have to double n and then subtract 1. So if we test that, a1 should be 1. So 2 times 1 minus 1, which is also equal to 1. So that checks out. The second term should be 3. So 2 times 2 minus 1, again, that's 3. So that checks out. and you can continue to do this. Okay, and all of them will end up checking out. Okay, so in this case, we worked from the sequence down to the rule. All right, and this AN, that's our answer. So again, I'm going to pause real quick. If there are any questions, now would be a great time to ask. Okay, so in this red example, there are two things we need to look out for. And the first thing to do in all of these is just to take a quick step back and look at the entire problem. All right, so you should notice right off the bat that we go from positive to negative to positive to negative. So we're switching signs. All right, so there are really two different problems here. The first is to identify how to make your signs switch in a positive, negative, positive like pattern. And then the second part is to get the magnitude correct. So the 2, the 5, the 10, and the 17. Okay, we're still trying to get from our blue number, our term number, down to our red numbers. Okay, but there's really two different ways, or two different things that we have to do. So again, the sign and the magnitude. So if we do sign first, anytime you see a sign change between each term, it's going to be -1 to some power. Okay, but if we just test that, for our first term, we'd have -1 to the first power. Our second term would be -1 to the second power. Third, -1 to the third, and so on. Okay, and if we do that, our first term would be negative, our second term would be positive, our third term would be negative, and it would continue that pattern. Okay, but on our actual sequence, we start with a positive and then go positive, negative, positive, negative. Okay, so just having n here isn't quite correct. So what we have to do is we have to offset that pattern by one place. Okay, so we just add 1 to our n value. So then if we add that, or check that, we get positive, negative, positive, and then negative. Okay, so that's the first part of our rule. And that boxed green. Okay, so that is part of our answer. And then our magnitude, again, we have to just take a step back and look at just the red numbers. So we don't have to worry about the sign right now. We just have to worry about the actual numbers. So 2, 5, 10, and 17. And again, if I do that, I notice that if we square each of the numbers of the term, we're going to get really close to the term itself. Okay, so 1 squared, that's going to be 1. 2 squared, that's going to be 4. 3 squared, that's going to be 9. 4 squared, that's going to be 16. Okay, so in each case, we're only 1 away from the actual magnitude of that number. Okay, so what we need to do is we need to take the number of the term and square it. And then when we do that, we're just one away, so then we have to add 1 to that value. Okay, so that would be the rule for our number, and we can check that by plugging in the numbers of the term. And in this case, again, we're just trying to find that magnitude. And that checks out. Okay, so our actual total rule, our final rule, are both of these two things combined. Okay, so again, I'm going to pause for a second. Are there any questions over what you see on your screen? So far in the previous examples, we've only really been dealing with explicit sequences. So those are sequences where there's an explicit rule to find each term, which doesn't depend on anything else. It only depends on the number of the term. Okay. Some sequences, though, are recursive, which means that each term is defined by terms previous the one you're trying to actually look at. So explicit, there's a specific rule for each number, whereas recursive is you need different terms previous that in order to find the next one. A great example of that is the Fibonacci sequence. Okay, so there's a kind of a good representation of the Fibonacci sequence highlighted here. All right, and this is found in a whole lot of different places, from spirals in a hurricane to spirals in a galaxy to facial features to numbers of petals on a plant to number of branches in a tree. Like it's found in a ton of different places. And the rule for the Fibonacci sequence is that the first two terms, so A0 and A1, are both 1. And then every term after that is the sum of the previous two. Okay, so that is, by definition, recursive because each term depends on the two before it. So if we were to find A2, A3, and A4, and A5, all we have to do is sum the previous two terms. All right, so in this case, and this is a good place to say this, your subscript, your number of your term, isn't always going to be n, right? So in this case, it's k. So A2 is going to be A2 minus 2 plus A2 minus 1. Which is A0 plus A1. Which if you add those two things together, you get 2. The third term is the sum of also the previous 2 terms. So it's the sum of A1 plus A2, which is 1 plus 2, which is just 3. The fourth term is the sum of the second term and the third term. Which is equal to 5. And then the fifth term is the sum of A4 and A3. All right, and it keeps following that pattern as long as you want it to. Okay, so again, there are 2 different types of sequences. There's explicit, in which case there's an explicit rule for each term. And then there's recursive, where each term is defined by previous terms to it. So again, I'm going to pause. Are there any questions about what you see on your screen? And this spiral, this is just a representation of the Fibonacci sequence. It's nothing you need to know. It's just, again, a representation. So another example of this, this is directly from your book. This is number 65 and page 648. So if you want a couple of other examples of this, it's a great place to get it. It gives you that the first term of the sequence is 3, and then every other term is 2 times the term before it minus 1. Okay, and I want to find the first 5 terms. So A2, the second term, can really be written as A1 plus 1. So it's 1 after the first term, right? Because we want it in this form, AK plus 1. And if we write it that way, we can rewrite it as 2 times A1 minus 1. Which then is just equal to 4. Okay, and then we do that for A3. So we can rewrite A3 as A2 plus 1. So then this is 2 times 4 minus 1, which ends up being 6. And then we can keep doing that. So sequences can be rewritten explicitly or recursively. Some sequences must be rewritten only recursively, kind of like the Fibonacci sequence. And some sequences can be written as both, right? This example, I'm not really sure if you can rewrite it both ways, but it's a great example of a recursive sequence. Okay, so again, two different forms, explicit and recursive. So far, that's all we've done. All right. Again, I'm going to pause there. Are there any questions over this example or anything that you've seen so far? What is k? K in this case is just like n. It's kind of the number of the term. So then ak plus 1 is really just the term after k, which is why I'm rewriting it as a1 plus 1, so that's the term after 1. a2 plus 1, that's the term after 2. a3 plus 1, that's the term after 3, and so on. And the last thing I want to go over today are factorials. All right. So a factorial is just a way to say that we're multiplying every number up until a given number together. All right. So the actual definition, if n is a positive integer, then n factorial is defined as n exclamation point, which is the notation we'll be using. So that says n factorial. And what that means is we're multiplying every number up until n together. Right, so if we look at a number line, we're multiplying every number up until n together. And then where the number before n, that's n minus 1, two numbers before n, that's n minus 2, and it continues like that. All right, so in this case, n we don't really know. And there are a couple of rules that we should know, and not many, but they kind of work like exponents. So 0 factorial, that's just always going to be equal to 1. Right? Think of it as any number to the 0 power. It's kind of the same concept. Right? 1 factorial, again, is just equal to 1, because that's 1 times nothing else. 2 factorial is 1 times 2. 3 factorial is 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4. And 5 factorial is 1 times 2 times 3 times 4 times 5. Okay, and if you simplify those, you'd get those numbers, but they follow the same pattern. Okay, but I'm not going to just give you a number factorial. You plug it into a calculator and you get an answer. All right, rather you'll get something that looks kind of like this. And I'll ask you to simplify. All right, so this says 8 factorial times 3 factorial over 9 factorial. And I'll ask you to simplify. And usually what that entails is rewriting each number based off its definition. So 8 factorial we can rewrite as 1 times 2 all the way up to 8. Three factorial is 1 times 2 times 3. And then 9 factorial is 1 times 2 times 3 all the way up until 9. And then we can simplify just by canceling out common factors. Right? So everywhere you see something kind of repeat itself, you just cross it out. So the 1's cancel, the 2's cancel, the 3's cancel, the 4's, the 5's, and the 7's and 8's. So then what we're left with is 1 times 2 times 3 over 9, which is 6/9, which is just 2/3. And then that would be our answer. So all a factorial is every number up until a given number multiplied together. So again, I'm going to pause there. Are there any questions about what's on your screen? All right, I want to do one more example, in this case with variables instead of just numbers. All right, so in this example in green, we have n plus 1 factorial divided by n minus 1 factorial. Okay, so again, we have to split this up into two different parts, each by its definition. So we need n plus 1 factorial, which again, if we look at a number line, we have some number n plus 1 that's just a number. We have to multiply every number up until that together, including the number before n plus 1, which is just n, and the number before that, which is n minus 1. Okay, so we can rewrite our numerator as 1 times 2 times 3 all the way up until n minus 1 times n plus 1. And then in the denominator, we can rewrite n minus 1 factorial as 1 times 2 times 3 all the way up until n minus 1. And then we can cancel out common factors. It's the 1's cancel, the 2's cancel, the 3's cancel. Everything up until n minus 1 cancels. N minus 1's cancel, and we're left with n times n plus 1 in the numerator, which is just n squared plus n. Okay, so you're not always just going to get numbers here. You're going to get variables as well. Okay, now I don't have any homework over this. The only homework I have is over the first two things that we did, which are sequences and series. Okay, but this will be important. It will show up on your test. I will eventually get homework out on it. It's just not going to happen just yet because I'm trying to figure out a good way to do it. All right. So your homework is W1 and W2 all the way up until 100. Okay, and that's, again, that's the first two things that we did. All right. So I'm going to leave this open for a minute or two. If you have any kind of general questions, you can ask. After that, I'll go over to Teams, I'll start a meeting, and I'll give you guys a little bit more specific help. Is it the pre-calculus section? Yes, it's the pre-calculus section of IXL. Okay, so I'm going to close this. I'll go over to Teams. I'll start a meeting if you need specific help, and I will see you there.